Right now, deep in the outer solar system, a world nearly 6 billion kilometers from the Sun is doing something scientists once thought was almost impossible. Liquid nitrogen may be moving through cracks beneath Pluto's famous heart-shaped glacier. Pluto is smaller than Earth's moon. Its surface temperature can fall to around -230 degrees Celsius, and sunlight there is roughly 8,000 times weaker than it is at Earth. By every simple expectation, Pluto should have cooled into a frozen, inactive world billions of years ago. But when NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed something completely different. The images showed enormous mountains made of water ice, flowing nitrogen glaciers, methane ice dunes, a thin but dynamic atmosphere, and enormous structures that appeared to be cryovolcanic in origin. The most famous feature is Tombaugh Regio, the enormous heart-shaped region whose western lobe is Sputnik Planitia. Much of Sputnik Planitia appears remarkably young and smooth, suggesting that Pluto has resurfaced itself relatively recently. That immediately created a major question. How can such a small world remain geologically active after 4.5 billion years? The answer begins deep inside Pluto. When Pluto formed, radioactive elements such as potassium-40, uranium-238, and thorium-232 became trapped inside its rocky interior. These unstable atoms have been decaying ever since, releasing energy as heat. Potassium-40 has a half-life of about 1.25 billion years. Uranium-238 has a half-life of about 4.47 billion years. These aren't brief bursts of energy. They are extraordinarily slow nuclear processes that have been running for billions of years. Pluto's rocky material acts as a long-term heat source, while its layers of ice help insulate that heat. Scientists believe Pluto is differentiated, with a rocky core surrounded by layers of water ice and volatile ices such as nitrogen, methane, and carbon monoxide closer to the surface. That internal structure may allow a subsurface ocean to survive beneath Pluto's frozen exterior. And ammonia could make that ocean even easier to maintain. When mixed with water, ammonia lowers the freezing point, allowing liquid mixtures to remain stable at temperatures far below the freezing point of pure water. So while Pluto's surface is brutally cold, conditions hundreds of kilometers underground could be dramatically different. But Pluto's internal ocean may not be the only liquid involved. Recent research has raised the possibility that liquid nitrogen has moved upward through fractures beneath Sputnik Planitia, producing surface patterns that resemble wetting features seen on Earth's glaciers. If confirmed, this would be remarkable because it would mean Pluto isn't merely preserving evidence of ancient geological activity. Its surface may still be changing today. The proposed process begins deep beneath the nitrogen glacier. Heat from Pluto's interior can warm material beneath the frozen surface. Under the right pressure and temperature conditions, nitrogen could become liquid beneath the glacier. That liquid could then move through fractures and conduits in the ice before reaching shallower regions. At the surface, it could leave behind dark patterns that reveal where material recently emerged. In geological terms, recently can mean almost unimaginably young. Sputnik Planitia itself may have been resurfaced within the last million years or so, based on models of convection and surface overturn. That means Pluto's famous heart may not simply be an ancient frozen scar. It could be part of an active geological system that is still evolving. Then there are Pluto's enormous cryovolcanic structures. Right Mons rises several kilometers above the surrounding terrain and stretches roughly 150 kilometers across. Its broad shape and central depression have been interpreted as evidence of possible cryovolcanic activity. Picard Mons is even larger, rising roughly 7 kilometers above its surroundings. These structures are fundamentally different from Earth's volcanoes. Instead of molten silicate rock, cryovolcanism involves volatile rich materials such as water, ammonia, and other ices or slurries moving from the interior toward the surface. Their existence suggests that Pluto retained considerably more internal energy than scientists once expected. And there is another important clue. Some regions associated with possible cryovolcanism contain water ice mixed with ammonia-bearing compounds. That combination is significant because it could represent material originating from Pluto's deeper interior. In other words, Pluto's surface may contain chemical fingerprints of what is happening hundreds of kilometers beneath it. This changes the way we should think about the Kuiper belt. For decades, the region beyond Neptune was often imagined as a cold collection of ancient leftovers from the formation of the solar system. But Pluto has shown that extreme distance from the Sun does not automatically mean geological death. Triton, Neptune's largest moon, has shown evidence of active geysers. Other distant icy bodies have also raised questions about whether internal heat can survive far longer than previously assumed. The deeper lesson is that radioactive decay can turn a seemingly frozen world into a long-lived geological machine. There is no giant furnace inside Pluto. There is no powerful sunlight warming its interior. Instead, billions of years of tiny nuclear decays are adding up. One radioactive atom decays. Then another. Then another. And another. Over geological time, that microscopic process becomes enough energy to influence glaciers, ice layers, atmospheric behavior, and possibly even a hidden ocean. That is what makes Pluto so extraordinary. The world we once imagined as a dead ball of ice and rock turned out to have mountains, glaciers, dunes, weather, an atmosphere, possible cryovolcanism, and potentially a liquid layer buried beneath its crust. And the discoveries did not end with the New Horizons flyby. Scientists are still analyzing the spacecraft's observations more than a decade later, looking for clues hidden inside the data. Pluto's complexity has also reignited a much older debate. Should Pluto really be classified as a dwarf planet? Under the International Astronomical Union's 2006 definition, a planet must orbit the Sun, have enough mass for its gravity to make it approximately spherical, and have cleared its orbital neighborhood. Pluto satisfies the first two requirements but not the third because it shares the Kuiper belt with many other objects. But some planetary scientists argue that orbital dominance is not the only meaningful way to define a planet. They point instead to geological complexity. A world with a layered interior, an atmosphere, active geology, mountains, glaciers, possible subsurface liquid, and changing surface processes may seem fundamentally different from an inert asteroid. That debate is unlikely to disappear anytime soon. But whether Pluto is called a planet, dwarf planet, or something else, its physical reality does not change. It is an active world. And perhaps that is the most important discovery of all. Pluto sits billions of kilometers from the Sun in temperatures cold enough to freeze almost anything we encounter on Earth. Yet deep beneath that frozen exterior, radioactive elements have been quietly releasing heat for 4.5 billion years. That ancient nuclear energy may still be driving geological processes today. A tiny world at the edge of the solar system, once dismissed as frozen and forgotten, may contain a hidden ocean, moving glaciers, possible liquid nitrogen pathways, and an interior that refuses to completely cool down. Pluto isn't simply a frozen rock at the edge of the solar system. It is a world that has been quietly evolving for billions of years. And even after New Horizons transformed our understanding of it, Pluto may still have more secrets buried beneath its ice.